This video lecture will continue the discussion we began earlier about waves that are traveling down strings. The topic this morning is standing waves. This is not a standing wave. We'll get to that soon enough. This is just a pair of pulses traveling along a string. I won't show the entire train of pulses. Won't show the entire wave. Just enough of it to convey to you the idea of a wavelength. The distance between consecutive peaks, you can call them maxima, is the wavelength lambda. It's also the distance between the beginning and end of this portion of the wave, shown in red. This distance there is the same as that distance. So that's one full wavelength as indicated here. Keep that shape in mind when we look at the picture below. What I show here is a string aligned there, tied at one end at a wall. The other end is being oscillated at a certain frequency. At this particular frequency, what happens is that the wave traveling to the right reflects in such a way that there's what we call constructive interference, that the peaks overlap and the valleys overlap. What you have here shaded within this loop, I call it, is a blur of string. The string oscillates like this. Well, that portion of the string is doing this portion is doing that, and this is doing that. So it's this and that. Now, I refer to each of these clam-shaped figures as a loop. There are 5 such loops spanning a distance equal to the length of the string, shown here labeled L. The distance between this point and that is one full wavelength, as shown up here in red. Same wavelength here. Notice that 2 of these loops span a distance equal to lambda, so we can recognize that the loop width, this or that, and that, is equal to 1/2 of that wavelength, 1/2 lambda. There are some points of interest along this wave. There are places along this wave which are called nodes. Those are places where the string is not moving at all. Other places oscillating ferociously, but there are places called nodes where there is no vibration. At those places in between 2 nodes, there is an antinode where very significant oscillations taken place. The reason this wave will be called a standing wave is that there are certain points, nodes, along the length of the string that are standing still, not oscillating. Now, let's discover what frequency will cause this particular pattern, this particular standing wave, given that in this example problem, we let the length of the string be 1.5 meters. We let the speed of waves on this string be 3 meters per second. And we ask, what will have to be the frequency that will allow this to happen? Those arrows there represent the oscillation of this end of the string. We treat this end of the string as if it were a node, a place of no movement, even though it will be moving a little bit. Not much compared to the large sweep that occurs here. This allows us to treat this end of this loop as a node, and therefore we can legitimately count this as a node along with the 4 others for a total of 5 loops. Well, back to this. We're looking for the frequency of oscillation at this end that will cause this pattern to exist. Well, we use the fact that the sum of these 5 widths 1, 2, 3, 4, 5 must equal the length of the string. The distance there is L. The sum of those 5 loop widths is equal to L. Here are the 5 loop widths, 5 times lambda over 2, equaling the length of the string. So we solve for lambda and get 0.60 meters. And now we use the very important wave equation, which is not repeated here. You should memorize it. The wave equation is the following. Lambda times f equals a speed. Lambda f equals v. There's your lambda we just found, 0.60. There's your f unknown. There's your speed, 3 meters per second. Solve this equation for f, and we get 5 hertz. Final answer. Let's work another problem. I show a string that is 9/10 of a meter long. It's tied at the wall there. An oscillator is there, causing small movement there, but nevertheless gives rise to large movement at the antinode. We wish to determine what frequency will cause this particular pattern with just one node. We'll let the speed of the wave be 3.6 meters, and what we're looking for are the 2 lowest frequencies that will cause a standing wave. Another way to say it is that we're looking for the 2 smallest frequencies that will cause what we call a resonance, a reinforcement type of overlapping of an advancing wave and a reflected wave. All right, so we have that lambda over 2, the width of this one loop, equals the length of the string between there and there. Solve for lambda, we get 1.8 meters. Once again, the wave equation, lambda times f equals speed. Lambda f equals v. Lambda 1.8, unknown f, equals 3.6 for the speed. Solve for the first of the 2 frequencies, which I'll now rename as f1. We get 2 hertz when we divide 3.6 by 1.8. Now, the next lowest frequency will be the one in which there are the next fewest number of loops. The lowest number of loops you can ever have in a standing wave is 1, then 2, then 3, then 4, then 5, then 6. So the next lowest frequency will correspond to a standing wave with 2 loops. Each loop will have a width of lambda over 2. We have 2 such widths, which must add up to the total length of the string, which is 0.90. The 2's cancel, and lambda equals 0.90 meters. Again comes the wave equation. Lambda times f equals speed v. Lambda is 0.90, f is unknown, solve for f. Final answer, 4 hertz. And I'll label that second of the 2 frequencies as lambda as f subscript 2. Now, what I would invite you to do, and I will not do it for you, is to discover what is the third lowest frequency that will resonate on this particular string, whose length is that, and whose wave speed is 3.6 meters. What you will find for this third frequency, you could call it F3, that you would find that the frequency that will resonate is 6 hertz. And then you do it for the 4th lowest frequency, repeating the same kind of calculation, and you'd find that the 4th frequency is 8. And then if you were to calculate several of these lowest frequencies, this is what you would find. F1 is 2, F2 is 4, F3 is 6, F4 is 8, F5 is 10, F6 is 12. You get the idea? Each frequency in the sequence is 2 hertz higher than the last one. The lowest frequency in a list such as the one we're talking about is called the fundamental frequency, the lowest frequency. The next highest frequency, F2, is called the second harmonic frequency. Fundamental frequency, F1, is called the first harmonic or first harmonic frequency. So you have this vocabulary, these vocabulary terms to be acquainted with. There's the first, second, third, and fourth harmonic frequencies. Say it again, first and second, third, fourth harmonic frequencies, where the first harmonic frequency is also called the fundamental frequency. What about the second harmonic frequency? It has a different name also. The second harmonic frequency is sometimes called the first overtone, the first over frequency, the first frequency higher, or the next higher frequency from the fundamental or the first. And perhaps you will just choose to study the notes where I go into somewhat more detail in a discussion such as this. Let me urge you that when you come to the portion of the notes where we talk about standing waves, there is an excellent video that shows the standing waves. Don't fail to look at that video. It won't be included in the list of video lectures that I create, a list that has links at the top of part N notes. It's a link to the video that occurs in that portion of the notes dealing with standing waves. I hope all of this was helpful. When we next come to class, the next video lecture will deal with sound waves. That's all for now. Thanks for coming.